Okay, so I'm recording now. The first question of the night is in the chat. And I've kind of set this up, by the way. You guys don't actually have to ask questions. I have kind of a plan in mind of some things I'd like to cover. So if I'll answer any questions you have, of course, but if you kind of just want to sit back and look at some examples, I have a plan for that as well. But anyways, to answer question number one, what is KP and how do you do it? How am I going to do this? Let me open up my PowerPoint and I'll share just like a blank screen so I can write on it. I'm not going to go through notes or anything like that because it just take too long flipping through all of the notes. So first question, what is KP? Well, we didn't really deal with KP too much. If you look through your notes and you look at some of the worksheets, you will see KP. But for us, wink, wink, we're really going to focus on KC. KP stands for pressure, and you would only use gases. So it's still the same thing. You know, if I had like A gas plus B gas is in equilibrium with, like, let's say 2C gas, you would just do it as normal, products over reactants. So C squared over A times B. So it's the same thing. You guys don't have to worry about that on your test tomorrow because we focused on KC and KW and KA and KSP. So it's KC, KW, KA, and KSP. But if you are wondering, you know, if you look through your notes and you saw KP, it just means pressure, and it's for gases. All right. Yeah, so as Abdul Rahman said, it's only for gases. And as Aman just asked, no, that's not going to be on your test tomorrow because we didn't do it in class. It was hinted at in your notes, but it wasn't, we did no examples. We didn't do any practice problems. So you just need to know the Ks in this corner here. KC, KW, KA, and KSP. Speaking of K, even like KB, you'll see a little bit of KB in your notes. We didn't do that either. I just hinted at it. So KC, KW, KA, and KSP will have you covered. They are all the same, by the way. All of them represent the exact same thing. It's just that the little letter, like the P and the C and the W, represent what you're calculating. So P for pressure, C for concentration, W for water, but they're all the same. Same formulas, everything. Okay, so well, again, I'm going to keep checking the chat. Okay, so 2 questions in the chat. I can't really tell you any definitions to memorize because I don't ask you to define anything. It's not my style of question. So the answer is you don't have to memorize any definitions. You should have understanding of terms if there was like a multiple choice, like, you know, if I asked you which way an equilibrium shifted, but like I will never ask you to define anything. Off the top of my head, if I could think of like one definition to know, it's what an acid is and what a base is. So an acid is definitely, you know, there's lots of definitions, but we've learned the Bronsted-Lowry definition. So an acid would be a chemical that donates a proton or hydrogen, and a base is a chemical that accepts it. But I'm not going to ask you guys any definitions. You know, like you won't see a question tomorrow that says define KW or something like that. Like, no. I have another private question, so you guys probably can't see this, but it says what is Ka? And we did Ka back in chapter 4, so I guess only a week or 2 ago. Ka is equilibrium constant for acids. Aman asked another good question. Will the question mention which K to use? Yes, sorry, I shouldn't say obviously. What I mean is I will definitely tell you if I want KC or KA. And guys, remember, they're all the same. It's products over reactants. We never use solids or liquids. All right. Guys, keep asking questions. You can load up the chat with as many questions as you want, and I'll get to them as I read them. But I don't know if you saw this at about 5:24. So 5:24 p.m. I uploaded a sample. It's an old one. I guess about a year or 2 years old now. But this is a test that covered units 3 and 4. This is a bit long. This test is longer than the test that I would typically give by a question or two. But this is good practice. And after the tutorial tonight, I can send you guys the answer key to this. Okay, so let me check the chat. Oops, sorry, let me share my screen. I don't know if I was sharing my screen or not. But let me check the chat, and then I'm going to look at some of these questions. I won't have time to do the whole test, but I'm going to kind of give you some key important wink wink type of questions that you should definitely know for tomorrow. And sorry, I'm just trying to open up my chat here. Ooh, okay, so yes, we're going to start doing the sample now, Noor. Iman, I'll be on campus for your test tomorrow, but I won't be in my office. So if you have any questions, send me an email. But I am, unlike last time, I didn't get or come in contact with somebody with COVID this time. So I'll be there. I'll be in the classroom with you tomorrow. But if you have questions, I recommend emailing me. And Noor, I will start doing the sample right now. It's just I want to check one thing and then I'll start the sample. Somebody just asked if I could upload the data book, and I thought that I did. But if I didn't, I can have it uploaded after this session. If I can't find it, and I'm just going to look for one quick second, if I can't find your data booklet, I will send it to you with the answer key. Yeah, I don't see it. Course information, no. Okay, so Mana, I will upload the data booklet, or what I'll probably do is email it to you after this class. All right, let's get started with the sample. Oh, Abdul Halim says it's in with the CH1121 course information. So I'm going to get started with the tutorial now, but you can look for it there. And again, if you can't find it, I can easily send it in an email. All right, let's get started. So part A, let me zoom in a little bit. This is multiple choice. My test has 10 of them. So you'll see some of these in some way, shape, or form tomorrow. The reaction to HF goes to H2 plus F2 has a rate of 15 moles per liter per second. And it says at time equals 0, the concentration of HF is 0.95. What time will HF be 0.41? This is kind of like a half-life type question. So let me just do something 1 second before I get through the answer to this. Just 1 second, guys. Okay, sorry, just making sure everything's shared properly. Oops. There we go. Okay. So this question, the reaction here, I don't know if I can write on this. That's what I was just trying to do, but I'm going to have to do it the old school way. Here's my reaction. Here's my initial rate. Here's my time. And here are my concentrations. So my goal here is to find the time in this equation. This is actually a pretty tough question. This is definitely not my test. This is pretty challenging. So the formula for that is rate is equal to change in concentration over change in time. Okay, and the reason that this is so hard is not because of the chemistry. This is like the first equation we learned in chapter 3. It's because of the algebra here. And I'm going to run out of room if I write too much. All right. Oh, I hate this. I hate writing in the Zoom app. I was trying to open this up in PowerPoint, but it's not working for me. So you'll just have to bear with me writing in the Zoom app. It's not very nice. Okay, so this ends up being kind of like a fill in the blank type question. The rate is 0.15. My change in concentration is final minus initial. So I would say 0.41 minus 0.95. Sorry, that looks like a plus sign. That's supposed to be a 1 with a minus. Let me get my eraser here. There we go. Let me clean that up a little bit for you. Okay, so rate is change in concentration. So it's fine, the final concentration minus the initial. 41 minus 0.95. That's a 9, not a G. And then it's T final minus T initial. So T final is what we're looking for. T initial we are given as 0. So T final is here minus T initial, which is 0. Okay, so now we just solve for this. And again, this is a tricky one. This is for the first question on your test number 2. I definitely didn't teach this test. This is a tough one. And again, it's not because the chemistry is hard. It's now we have to solve for our final time in our rate equation. So this becomes like a math problem, not necessarily a chemistry problem. But looking at this, it's actually not that bad mathematically. So the only problem I'm having is I don't have enough room to write on the PowerPoint. So, or not on the PowerPoint, but on the PDF. Oops. I'll read the chat in a second there. I'm just doing some calculations. Boop, boop, boop. Aha, I knew that was going to do that to me. Just guys, I'm using my calculator now. Just a reminder, I mentioned this in the chat. Make sure you bring your calculators tomorrow. I only have one, and with COVID, I'm not really supposed to be lending out things. I mean, I can hand sanitize it or whatever, but try to bring your own calculator if you can. Okay, so this looks pretty simple actually now. We've kind of simplified this out. Let me just check the chat. Oh yeah, I got some good suggestions in the chat. You can just use the multiple choice to fill in the answers. Yeah, anyways, we would solve for this value here and see what our answer gets. And somebody had mentioned you could use the answers to the multiple choice to predict this, or not, predict's not the right word, but to infer, I guess, the answer to this. But realistically, oops, I hate writing on this. The answer is here. And you would solve for your final time, T final. So there's a little bit of algebra here. What it ends up being when you rearrange it is your final time is 0.54 over 0.15. And you would get 3.6. This is a tricky one. I wouldn't worry too much about that one for tomorrow, but that's a good practice one because it really shows if you can kind of rearrange some of these equations. So yeah, the answer to that one is 3.6 seconds. And again, I solved this equation here. All right. Let's look at another one. Now, this one's a good one. This one's a pretty standard question. Just hold on one second. I just want to write something down here before I get started. I don't have my data booklet, so I'm just kind of writing down any molar masses or formulas or anything I need. Okay. All right, let's look at number 2. Now, the reason I'm picking number 2 is because we haven't done one like this in a while, the half-life. The half-life of this chemical radon-228 is 7 years. Now, again, what that means is after 7 years, the amount of this chemical would be reduced to half. So if a watch contains 2.16 milligrams of this isotope, what would remain after 21 years? Okay, so this is a little bit easier once you know your half-life formula. This formula will be given to you, okay? And the formula is your mass total is equal to your mass initial times 1/2 to the power of your total time over your half-life. And it looks a little complicated, but it's actually a pretty easy formula. So again, MT is your total mass, kind of what you're left with after time. MO, or what you would say in physics, is M naught, which means your initial mass. And then the time T is your time, and T 1/2 is your half-life. So I'm just going to put my numbers in. This is a much better question, by the way. This is a lot more like for a multiple choice. I'm really looking to see you guys do kind of one step, one thing. And this is really quick because I can just put in my formulas or my equations, my numbers is what I'm trying to say. I'm trying to write and talk at the same time. Now, the only thing you might get confused with here is getting the half-life confused with the time. The half-life is 7 years, the time is 21. So this would become 21 over 7. Basically, what's happening is we're going to see this happen for 3 half-lives. 0.5 to the power of 3. Sorry, I'm talking to myself. And I end up getting 0.27 milligrams. Pretty straightforward. And actually, I mean, guys, when you're looking at your answer here, or you're looking at your possibilities, get rid of D right away. D doesn't make sense. How could the mass go up? This is a radioactive isotope that's losing mass. That's what half-life is. It can't gain mass. That's not how isotopes work. So and again, law of conservation of mass. It's not me saying it loses mass is not really fair. It's just decaying or breaking down into other things. All right, let me check the chat and I'll keep moving on. All right, A, that's really good. Yes, guys, I just got a private message. Bring your face shields for tomorrow and your masks. We're going to socially distance. As you know, we're in the lecture theater like we were in before. Well, you guys were there. I wasn't there. But bring your shields and definitely bring your masks. Okay. Which is true? So I'm just reading number 3 here. I hope you guys can see my screen. What is true? I have this equilibrium. Mass of H2 equals mass of NH3. Sorry, I'm just kind of like thinking about which one of these could be true. So I have an equilibrium here. It says mass of products equals mass of reactants, mass of N2 equals mass of NH3, mass of H2 equals 3 times mass of N2, and the mass of NH3 remains constant. What do you guys think for this one? C, I'm getting a few C's. This is I think this is a bit ambiguous, but I can give you some hints about this one. This is like, I know what this question is trying to ask. This question is trying to ask, what's true about equilibrium, but it's kind of leaving out the key wording here. What we're going to assume for this is that we're going to assume that this is at equilibrium, meaning, we haven't left it. It's not being changed by us. Like, this is not a Le Chatelier's principle. And one thing I want to tell you guys that's really important to know is at equilibrium, the forward and reverse rates are the same. Now, that's not part of your question here. A, B, C, and D aren't mentioning rates, but when a chemical is at equilibrium, you can think of it as being stable. The forward rate equals the reverse rate. Okay, so yeah, this test, this is a toughie. I'm kind of feel bad I picked this for a sample, but this, if you can do this, you guys will laugh at mine and Mr. Robbins' test tomorrow. This is a good but tricky question because it's not clear what it's saying. So at equilibrium, the forward rate and the reverse rate are equal. So what it's trying to get you to understand is when something's at equilibrium, it could be like temperature equilibrium, it could be chemical equilibrium, it's staying constant. Nothing is changing. And that's why D is the answer. I'll tell you what, though, I would put a star by what I wrote here. At equilibrium, the forward rate is equal to the reverse rate. That's something you should definitely know. And this multiple choice is kind of like trying to ask a weird way around this, trying to like get you to really think about it. So like, how come A isn't true? Well, we don't know the mass of the products and reactants, and we don't know the value of K. So I don't know if this is favoring products or favoring reactants. So A, B, and C, I can't answer because I don't know the mass of anything. But I do know that a chemical at equilibrium, when left alone from humans, will stay the same. Number 4, this is a much better one. Number 4 is a normal multiple choice. What is true for all acids? Easy, okay? This is straight from the definitions or the, I guess, facts about acids and bases at the beginning of chapter 4. We learned a couple of facts about acids and bases. So acids taste sour, bases taste bitter. Bases feel slippery on your skin. Bases would have a high pH. Like I'm kind of listing off some facts here. And what I need to do is find the one that's true for all acids. Well, let's see. So let's check off everything in this list that is true for an acid. So yes, they definitely taste sour. They do turn litmus paper red as well. I'll make a little cheat sheet for you guys on that in a second. Okay, acids, do they taste bitter? No. Do they turn litmus paper blue? No. Are they slippery? No. They do react with metals though. They're not slippery and they don't have a high pH. So the only one here that has everything true about it is A. And I want to give you a little reminder because this is something I always forget. Well, no, I guess I should say this is something I never forget because I've made up a little rule to remember this. B for base turns blue, BB. Any paper, litmus paper, red or blue, that you put into an acid or base will go blue. So if you put blue paper in base, it will stay blue. If you put red paper into base, it will turn blue. Base turns blue. And that must mean, well, there's only one other color. Acid will always turn red. So red paper stays red, blue paper turns red. And I've always remember that. I haven't picked up a piece of litmus paper in 15 years, but I remember that's not true. I guess we do it in your lab, but I just remember that this paper will be blue, 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 blue in a base. All right. Thank you, Iman. Just reading the chat here. Yeah, I think you guys will like my test. Well, it's mine and Robin's test. I think you'll like it. It's a little bit, it's straightforward. But yeah, as I think it was Aman just mentioned, back up in question 3, the key word you had to pull from that was constant. And that's what equilibrium means. It's like it's staying constant. All right, let's keep moving. Oh, beautiful question. Beautiful. Which describes a Bronsted-Lowry acid? I couldn't pick a better question. This is a great, nice and easy multiple choice. Put a little winky face there. Now, this is like you guys really only learned one definition in my notes. So this is like a process of elimination to choose what you learned. If you read too much. You know, if you're like if you're watching YouTube videos or you're reading a textbook, you might have heard of different types of acids. There's Arrhenius, Bronsted-Lowry, and Lewis, and we didn't take time for any of them except Bronsted-Lowry. That's kind of like your classic first year chemistry definition, and it's useful to this day for myself. It's still a good definition. What you really want to look for when you see the word Bronsted-Lowry, you want to think about protons, or specifically that hydrogen atom. Remember in chemistry 1120 or 1121, we learned that hydrogen atoms, a chemical that starts with a hydrogen is an acid, and that's where the Bronsted-Lowry comes into play. So, HCl reacting with OH minus, the proton, which is an H plus, gets donated. Sorry, that should be H2O. You don't need to learn how to write the formula or anything. Don't worry about that. I'm just trying to explain to you what an acid and base, Bronsted-Lowry acid and base are. So an acid donates a proton, which means it gives it away, and a base accepts a proton. C and D don't fit in our definitions. We've never learned about this concept of dissolving to change the level of OH. It has to be A or B, and in this case, because it's an acid, it's going to be B. Acids donate protons. And just one more thing. I see the chat going crazy here. Like, think about it. Think about what acids are. So there's like HCl, HNO3, H2SO4. Acids have to be the chemical to give away the hydrogen. They are like, so what I'm saying is, if tomorrow you can't remember, you're thinking, oh crap, do acids take protons or do they give them away? Think about what an acid is. It's HCl, HNO3, HBr. It's the chemical with the hydrogen. It's going to give it away. Bases like NaOH, NH3, the letter H is not the first chemical. It's not going to be giving it away. I hope that helps. That's kind of how I always thought about this stuff. And yeah, lots of people are giving me the answer. That's beautiful. And somebody just mentioned, is a proton different than a hydrogen? That's a deep question. Like it depends on how you want me to talk about semantics. Okay, so like what I mean is word usage. You have to be really careful, because hydrogen, if you just said hydrogen to me, I could think of it as the atom, or I could think of it as the molecule, the molecular atom. So when you hear me say proton, I'm actually talking about the hydrogen ion. And guys, I'm spending time answering this because this is a good question. This is like the fundamental concept behind chapter 4, is we are following what a chemist might say a proton, but what we're actually looking for is a hydrogen plus. In an acid and base reaction, you're looking to find or follow the hydrogen. Where did it go? Who's taking it? How many hydrogens did it give away? Right? Remember, that's how strong an acid is. All right, I'm going to pick up the pace for 6 and 7 and 8 because they're very quick. And I'd like to do a couple of long answers. There's a few I can think in the back of my mind. Like, I think I definitely want to do, question 1, 2, and 3. I would definitely like to do with you guys because we haven't done chapter 3 in a long time. Guys, also looking at the rest of this test, the first 3 questions are very challenging, and then everything else is pretty standard. So I didn't mean to freak you out. I just found this test on like a hard drive. So I was like, oh, I'll throw it up online. What's the harm? And the first 3 questions are crazy. And then questions 4, 5, 6, 7, 8, 9, these are all really good, simple, multiple choice type questions. So you'll see when I go through these. how much easier they are. Like I know, for example, a lot of you just had no problem with question 4 and 5. Okay, question 6. The only reason you might not know question 6 is if you didn't remember what the conjugate base means. Conjugate, you can think of like its partner, its pair, and it's a base. So I'm looking for, like, split the chemical reaction in half. Feel free to share your answers in the chat, by the way. I'm getting a lot of responses tonight, so I might not be able to tell you if you're correct or not, but throw your answers in the chat. I'm splitting the left and the right into, like, the left and the right are going to be my acid and base, and the right, so that's the left side, and the right side are going to be my pairs, my conjugates. I'm not going to label them acid or base yet, but the chemicals on the left are my acid and base. The chemicals on my right are my conjugate or partner acid and base. So the first thing I want to do is figure out which is my acid and which is my base on the left side. And obviously, this has to be my acid and this has to be my base, because this is the only chemical with the hydrogen. Look at the other chemical, the chemical that I call base, the sulfite ion, SO3. It doesn't have a hydrogen. It physically cannot be an acid in chemistry 1121. In real life, who knows? But it can't be an acid. Well, now I'm halfway there. If I know my acid, the acid turns into your conjugate base. And that's it. That's what we learned in class. The acid turns into your conjugate base. Your base would turn into your conjugate acid. Takes a little bit of memorization, but it's not a very tricky question. And this is definitely something I would know. Yes, there's a question in the chat. Could an acid be, thank you guys, everybody, by the way, for answering question 6, and someone has answered question 7. But somebody in the chat just said, can an acid be 0 pH? Yes, acids can actually be less than 0, which I'll try to avoid. But yeah, acids can totally be 0. In some situations, you can get an acid that's like -1, but I will avoid that. I'll keep it simple. Okay, number 7. Whoops, number 7. This is another good one to know. Very quick and easy question. I'm looking for H3O in pure water. So I'm going to use my formula, Kw equals H3O plus times OH minus. Kw is a constant, which when I was teaching math a few years ago, they changed it on me, and now I can't remember it. I think it's 1.011 now. We added some extra decimal places to it. So this number here is a constant, 1.011 times 10 to the minus 14. And it's asking for H3O plus. And actually, I don't know why I'm writing the calculation down. We don't actually need this because it's asking for this in pure water. Pure water meaning it's completely neutral. And this is actually not even a calculation. You don't even need your calculation for this. It's B. This is from your notes.
So do we have to memorize this number?
No, this formula and this number are in your data booklet. This number, yeah, I hate saying that you have to memorize anything, but this is the concentration of acid and base in pure water. This is from your notes. There's like 2 or 3 slides on this actually. But pure water has a pH of 7, meaning it's completely neutral. So yeah, this is, again, that's a question from your notes. But I would know this formula that I crossed out. I guess I didn't mean to cross it out, but for me, you might want to know this formula here. And you don't have to memorize any formulas. I will give you everything. It's either in your data booklet, or if it's not in your data booklet, I will put it on the whiteboard or the projector. I don't know if there's a whiteboard in that theater, but I'll project it if I have to. Yeah, no whiteboard, I don't think. Yeah. All right, cool. Let's look at number 8. Number 8, beautiful question, pretty simple. These are the type of questions I can't, they're kind of tricky though, because this is again like another question about words. What describes a solution with pH of 6.8? And you really have to know the difference in English between very and slightly. Very, like, again, this is totally subjective, but the number is so close to 7. That's the key here. So something that's very acidic would be like around pH of 0, 1, 2. And I'm going to go on the extremes here. So I'm going to say very acidic is pH 0, 1, or 2. Very basic would be like pH 12, 13, 14. But anything around 7, again, this is all words. So, it's the difference between very and slightly. Anything around 7, I wouldn't feel comfortable saying that it's very. I mean, your blood is pH, I think around it's around 7. It might be slightly acidic. I can't remember now. Or milk is slightly acidic. Things like common everyday household chemicals, the blood in your body, they would be considered slightly acidic or slightly basic. Do you need to know the pH of milk or blood? No, absolutely not, because we give you the number here. So this is slightly something. What do you guys think? I spelled slightly wrong. Wow. What do you guys think? Is this slightly acidic or slightly basic?
Acidic.
Yeah. Perfect. I got a couple of people just saying C, which is slightly acidic. Yes, perfect. I know it's slightly acidic because it's close to 7, but it's less than 7. So let me write the answer here. Oops. C. All right. As Aman just mentioned in the chat, question number 9 is straight from the data booklet. You do not have to memorize number 9 at all. If you see question number 9 on your test tomorrow, it is a gift, meaning it's a freebie. You just have to look in your data booklet. And I guess I'll show it to you. I'm reluctant because it takes me like a minute to find it. And we're getting close to 7:13 or 14 here. But let me open up your data booklet and I'll show you where we can find it. Okay, here we go. That was quicker than I thought. I've been here for so long, relative to some people have been here for, if you guys have like, some of the physics instructors have been here for a long time, but myself about 8 years, and I have like 10 different versions of the data booklet because we keep changing it, and it's hard to find, but this is it. This is he. So page 6, you guys will be given this data booklet tomorrow. Oh, let me share my screen. I don't think I'm sharing it. You guys will be given this data booklet tomorrow. Don't bring your own in. So like really all you need to bring in tomorrow is your mask, face shield, pen, and calculator. Please bring your calculators. I cannot loan any out. I literally have one in my life, and I don't think I'm supposed to loan it out. I can bring some wipes or something, but just try to bring your own calculators, and do not bring a data booklet. I will bring it. So the question is saying which of these acids, and I know you can't see the question right now, but it's saying which of these acids are strong. Well, that's easy. The stronger acids in your data booklet are at the top, and the weaker ones are at the bottom. And it's organized in that direction, that strong is at the top, weak is at the bottom. So when I'm trying to find a strong acid, it has to be in the top of this list. And there's even a little line here to separate it. Okay, so let's see. Let's go back to your data booklet and check it out. I got too much open now. Too many tabs, too many things. Here we go. All right, so which is a strong acid? One of my favorites, kind of like your movie go-to, sulfuric acid. That's the one you always hear about, the hydrochloric or sulfuric. If you're watching like Mythbusters or movies, you hear about sulfuric, this one. And again, as Aman said, straight from your data booklet, no calculations, nothing. Question 10, straight from your data booklet, which is the weakest acid? Let me scroll down here. Oh, see, I love this one because I don't need my data book for this one. This is a good one. The weakest acid here would have the smallest Ka. Okay, so the lowest number of K, the smallest number of K would be my weakest. So let's check it out. I do like yeah, you're not wrong. I say I like pretty much everything or every chemical that I bring up, but I do like this question because we don't need the data booklet. And Abdul Rahman is mentioning, oh, so Abdul Rahman for KW, I don't really care what you use. It depends on what version of the data book you have. KW is approximately 1 times 10 to the minus 14. But in recent years, like if you picked up an old copy of the data booklet, we kind of change, we use more sig figs now, so it doesn't matter. I don't care if you use 1 or 1.011. It really doesn't matter. So yeah, as Abdul Halim says for this question, the weakest acid would have the smallest Ka, which would be, I'm going to pick up the speed a bit here. I'm just going to tell you, C. This is the smallest number. This is a number that has 9 decimal places in front of it, whereas the others have 7, 4, and 3. So this is by far the smallest. Hydrocyanic acid. Interesting. Not an acid I've dealt with before. Ascorbic acid is vitamin C, and formic acid you get if you squish a bunch of ants. Hypochlorous acid can be found in, it's like a bleach type of chemical. It's not bleach at all, but the hypochlorite ion is in bleach. And hydrocyanic, I got nothing for you. Don't know, never heard of it. But I always remember about formic acid coming from ants and when you squish up ants. All right. Okay. Yeah, okay, let's do 11 and 12 really quick. 11 is an easy question. I don't want to say it's worded difficultly, but it's an easy question if you know how to set it up, and it actually hasn't been set up for you. So what I mean is when you're writing a Ka expression, it's always the acid plus water. And the acid, of course, donates the proton to the water. But the key for this is that they're always aqueous except for the water. So guys, I'm going to leave this here like this because honestly, between chapters 3 and chapters 4, you should be comfortable with writing Ka. Ka is the equilibrium constant of acids. I had a student right at the beginning ask me, what do you do with Ka? K is just K. The A only means that we're representing an acid. It's still the concentration of the products over the concentration of the reactants. Nothing has changed. Just remember, we do not put liquids in there. Guys, and anything I don't get done, I'm going to send the answer key out to you guys via email. So yeah, A, perfect. All right, this is a beautiful, I love this question. It's a classic question, wink, wink, wink. I've asked it myself a million times. The question is asking, like, what's the difference between the endpoint and the equivalence point in a titration? Now, you guys, I think you did your titration this week. Even if you haven't done it yet, it is in the notes. The end point is when the color of your indicator changes color. The equivalence point is when your acid and bases have completely reacted. So A is not the answer. A is what we would call the equivalence point. Whoa, I spelled that one wrong, didn't I? Forgot my V. Equivalence point. And again, equivalence meaning the acid and base are equal. The end point is what we can see with the naked eye. You know, we don't need any special equipment. It's like when the chemical turns blue. This is what's called the end point. Wink, 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 star, star, star. That's a good one to know, even for your final exam, knowing the difference between the end point and equivalence point. Okay. Let me check the old chat here and I'll show you a couple more. Again, anything I don't get finished tonight, very easy, or I shouldn't say easy, but you can check the answers on your answer key. But I definitely think in 9 minutes or 8 minutes, we can definitely get through 1, 2, and 3. And I'll kind of leave some of the acid ones for you guys to practice with. Definitely know your titration. So question number 5, again, I'm going to send the answers out to these, and definitely know number 4. Okay, but let me just quickly do 1, 2, and 3 along with you, but make sure you know 4 and 5, again, especially number 5. Okay, but let's do 1, 2, and 3 together. And the big reason I want to do these is because so many students get questions 1 and 2 confused. Rate law is not the same as equilibrium constant. So when you're doing a question on your test or on your final exam and you see an arrow, forget about capital K like KC. Don't do it. Don't write it. It's not meant to be there. And this is why I think like chemistry people or science people are evil, because the first part of chapter 3, we used a little k. And then in the second part of chapter 3, we used a capital or uppercase K, and they are not the same at all. So you have to know the difference. When do I use little k and when do I use uppercase K? Right? So what do? Well, look at the equation. If you see a single arrow, this is a rate question. This is little baby k, which is our rate constant. So let me read the question. The reaction is second order with respect to pH 3 and first order with respect to O2. The rate constant, little k. Now, guys, I don't care if your k looks big or small. You have to know the difference when you're calculating it. I'm not going to be like checking how many centimeters tall your k is to see if it's big. It's just be careful because they're not the same number. So this says write the rate law. Well, I know that my rate, and guys, it's been maybe 3 weeks since we've done this. Your rate is little k, which I'm going to erase that. Well, no, let me write that down, times the concentration of pH 3 times the concentration of O2, and I raise them to their orders, meaning the information that I give you in the question. So this reaction is second order for pH 3 and first order for O2. Now, this isn't really the full answer because I should also put in my K number. So 6.2 times 10 to the 2 times the concentration of pH 3 squared times the concentration of O2 to the power of 1. There's my rate law. Whew. Question B says, what is the overall order of the question? It's 2 plus 1 or 3. You just add up the overall, I shouldn't say that in the definition. You add up all of the orders of all the other chemicals. So if I have a second order and a first order, 2 plus 1, 3. Okay, I'm not going to do C because C is just plug and chug, meaning you just put the numbers in and punch it into your calculator. But let's look at a couple things in the chat because you guys are hinting on some good things. Aman and Abdulhalim, yes, for rate constants or rate laws, don't worry about the products. Products have nothing to do with how fast a reaction happens. Think about when you're cooking food, you're making a cake. The cake doesn't control how fast the recipe happens. It's how fast you can mix the ingredients, not the final product. So if rate is the speed of a chemical reaction, the product doesn't control it. It's how fast can you beat an egg, mix in sugar to the butter, etc. Right? We don't have to get into cooking, but it's all about the ingredients, not the product when you think about how fast something happens. And as Hadil says, third order. Now, guys, I'm not going to do the answer to C because, again, it's just busy work, but it would be 6.2 times 10 to the 2. And I would put in my numbers. And that's it. Just get your answer. And the unit for rate is always mole per liter per second. You can really get yourself worked up into a stressful situation trying to think about units for rate. It's just like kilometers per hour, but in chemistry life. So mole per liter per second. Okay, let me do one more. Well, I think I can do like 1.5 more. I do have to go soon, but I will put up the answers and this YouTube video tonight very shortly. I just want to show you why is number 2 different than number 1, and then give you a little heads up about question 3. Okay, and don't forget tonight or tomorrow morning to look at, on your own, look at questions 4 and 5. But let me look at number 2 here. Notice the big difference for number 2. Equilibrium. The minute you see equilibrium, forget about rate laws. Put them in the back of your mind. That's not the question. It's not a rate law question. It's an equilibrium question. Okay, so equilibrium constant expression, it would be my products over my reactants. Okay, I notice I don't put the solid in there. This is a pretty good question, isn't it? Gee whiz, this is worth 4 marks. You guys, I think, are really good at this. It says calculate Kc if the steel tank contains 5 kilograms of Si. That's a distraction. We don't care about solids, but you'd put these numbers in your equation. This is a good one. I like this question. This is quick, it's easy. We've done a lot of these examples in class. There you go. And then for question C, if K is bigger than 1, it favors products. Look at where the arrow is pointing. If K is less than 1, it favors reactants. This is a good question. That's the worst winky face I think I've ever drawn, but this is a good question. So part A, we calculated Kc. Well, sorry, no. Part A, we wrote the formula for Kc. Part B, we threw some numbers into that formula. And then part C, I told you or asked you to tell me if it was products or reactants favored. If K is big, it favors the products. If K is tiny, it favors the reactants. I always get the question, what if it equals 1? It won't, but if it did, it would be pretty much equal. It wouldn't favor either. And Hadil says this favors the product. So let me see. And I'll do one more little thingy and then I'll go. Or I have to go. But feel free to email me tonight or tomorrow morning. When I did this on my calculator, I got a small number. So for me, it favors the reactants. When I did this on my calculator, I got 0.46. Here, I got the answers here, which I'm going to share with you. Don't worry. Let's see. Yeah, so I got for question B 0.46, which means the reactants are favored. Okay, guys, finale, because I do have to leave in a minute. I'm meeting somebody else. It's not CNA related, but I promised a meeting with somebody at 7:45. So I have to leave and get ready for that. But let's just look at number 3. The reason I'm saying let's look at number 3, we haven't done this question in a while. And make sure you study and practice Le Chatelier's principle. This is a really good way to get a couple of extra marks tomorrow because it's not a very challenging question, in my opinion. You guys might hate this, but I've always found, 8 years of teaching at the college, this is one of the best questions for students. It's always 4 to 5, 5 out of 5. So just make sure you guys study this question. Watch out for a few things. If I ask you what a catalyst does to the equation, a catalyst never changes the equation. Some questions like, say, B and G are trick questions, meaning like we're changing the solid, we're crushing the solid into a powder, or we're adding solids. Remember, changes in K happen with temperature, concentration, or pressure. So, B doesn't change concentration, doesn't change K. F doesn't change concentration. We crush it into a powder. It might make the reaction faster, like a catalyst, but it doesn't mean it will shift K. The only way you can shift K is by changing the temperature, changing the concentration, or changing the pressure or volume. Okay, so adding a solid or crushing a solid into a powder, adding a catalyst is not going to change anything. So with that said, guys, I unfortunately have to leave you. I'm so sorry. Oh, okay, I can't answer that question. The question was on this slide here. Why didn't the volume or pressure change anything? What's going on with this? Well, remember, to look at pressure or volume, you count, this is a pretty tricky one, count the moles of gas. There are 3 moles of gas on the left, 3 moles of gas on the right, and because they're the same amount of moles, changing pressure or volume won't change it. Just remember, if you increase the volume, it will favor more moles. If you decrease the volume, it will favor less moles. Just have a look over your notes for that. And thanks, Abdulhalim, the beautiful explanation there. Have a look at your notes. You can send me some emails. I will be tied up till around 8:15 or so. I'm going to be meeting with somebody for about 30 minutes, but I can answer emails after that, and I will send to you guys the YouTube link and the answer keys to this. All right, guys, I do have to go, but thank you so much. Send me an email tonight if you have any questions. Take care, and I'll be in the exam or the test with you tomorrow. So I'll be around to chat with you guys before and after. All right, thanks everybody. Thank you, Noor and Aman and Abdulhalim, Abdullah, Ahmed, Hadil, everybody.
Mr. Wear your mask. Don't
Yes.
forget.
Oh, I won't forget my mask. There's no way. All right, I'll see you guys tomorrow. Bye-bye. Take care.